So we're going to learn how computers work in this video. And some of the things we're going to cover are circuits and switches, coding schemes, binary, 2 to the power of n. So that's 2 to the power of n, not 2n, even though that's not up at the top. 5 generations of computers, Moore's law, bits, bytes, kilobytes, megabytes, gigabytes, and terabytes. How do we measure bits? So I should maybe put that in there. Measuring bits. And what bits are, right? We'll learn what that is, and we'll learn about machine language. And then I'm also going to give you a resource for learning a lot more about computers. So you could come to YouTube, Todd McCloud, and if you go there, I'll give you this resource just right off the bat. And then come to playlists, and then you could go to even more. And then the playlists that you're looking for all begin with like week 01. So let's see. Here we go, like week 16, ethics, week 08, networks and networking, week 02, computer concepts. Like this one right here. So what I'm going to teach you is like pretty much what I teach in my introductory computer concepts course. And so you're going to get this stuff right here. But maybe you want to see a little bit more about how hardware works and the role memory plays and the different areas of computer remembering, like cache, registers, RAM, primary storage, secondary storage, volatile, not volatile, what all that stuff is. So if you want to check that out, you can come in and watch these like week 3 and week 4 right here. I'm not sure what week 5 covers, but week 2, right, that's what we're going to be talking about right now. But if you want more, you can watch week 3 and week 4. So that's a good resource for you. All right, so let's take a look at this, how computers work. This is the first thing you need to know. Computers run on electricity. And like that's just like the foundation. And at the end of this presentation, we're going to get back to this idea of the power switch. And you know, the power symbol in computers is this power symbol. All right, and that's the power symbol, universal power symbol for on or off. And what this is actually composed of is a 0 and a 1, because something can be off, 0, or it can be on. And this is the foundation of how computers work, right? Like computers run on electricity, and electricity can be either on or off. I know there's like dimmer switches too, and there's like states in between on or off. It's like dim, but let's just look at the discrete ends of that spectrum. Electricity can either be on or off. And based upon whether or not electricity is on or off, we can encode a message and we convey that message. Now that sounds confusing, but just think about, or it could be a little bit confusing, but just think about your porch light on Halloween. Whoa. Hopefully a light bulb just went on over your head. Your porch light can be on or off, right? And if it's on, what does it mean? It means come trick or treat on Halloween, right? And if it's off, it means, you know, we're out of candy. Hope you had a good time. Go to some other house, right? So with a light, with a single light, we have been able to encode and convey 2 messages. If that light is on, come trick or treat. If that light is off, go away, we're all out of candy. And that, my friends, is like, that's it. That's how computers work. That's it right there. So they run on electricity. Electricity can be on or off. And we can encode and store and convey. So we can encode, store, convey, meaning based upon whether or not, the light switch or the circuit is on or off. So when I use the word circuit, when I use the word transistor, when I use the word switch, all that means is that something is on or off, right? It's just some way of sort of turning something on or off or measuring if something is on or off. Yes, there are nuances between a transistor and maybe a transistor and a switch or a circuit, right? And definitely between transistors and silicon wafers and chips and vacuum tubes. But at its heart, it's like a light switch. That's all it is, right? Something can be on or off. Circuit, transistor, switch, on or off. So computers run on electricity. Electricity has 2 states, on or off. And if we have one light bulb like our porch, we can convey 2 messages, right? So, come on in, come trick or treat, or go away, right? So it could be that. And so we have coding schemes. So the first thing you need to know about computers, they run on electricity. Second thing is that we could create coding schemes based upon whether or not a circuit or a switch is on or off. right? So one coding scheme is like the porch light on Halloween. If we have 2 lights, and pause the video here, but if we have 2 lights, how many messages can be stored and conveyed, right? So just imagine you're sending some message to your friend across the street. You have 2 light bulbs, right? How many messages can you send to your friend based upon the configurations of on or off of those 2 light bulbs? How many messages can you send to your friend? So pause the video, think about that for a second, and see if you can answer it. And then here's the answer. 4. Right? Because they could both be on, they could both be off. One could be on, the other could be off, or vice versa. And so you could create your own coding scheme, and you could say, hey, the arrangements of these lights, if they're in this arrangement, they mean these things. And if you tell somebody that coding scheme, they can look at those lights, and depending upon their on-off configuration, they know what you're trying to convey. So if we have 3 lights, how many messages can we convey? Right? So pause the video, think about it, see if you can come up with the answer. And now here's the answer. We could convey 3 lights, we could convey 8. And the way we do that is the formula is 2 to the power of n, where n is the number of lights or the number of switches we have, right? So 2 to the power of 3 is 2 times 2 times 2, which is 2 times 2 is 4, times 2 is 8, right? 2 to the power of 4 would be 2, 4, 8. 2 times 2 is 4. 2 times 2 times 2 is 8. So 2, 4, 8, 16. With 4 lights, we could convey 16. With 5 lights, we could convey 32. With 6 lights, we could convey 64. With 7 lights, we could convey 128. And with 8 lights, we could convey 256. And you hear those numbers a lot around computers. And the reason you hear those numbers is because computers are base 2. They're binary. Right? And the reason they're binary, and we have binary digits, bits, right? Binary digits, bicycle, 2 wheels, biplane, 2 wings, binary, 2 digits, right? Binary digits, on or off, 0 or 1. And because it's binary, right, we've got 2 digits, and everything is multiples of 2. It's 2 to the power of n. Well, how many lights do you have? Right? I have 3 lights, I can convey 8 messages. I got 2 lights on my porch, I can convey 4 messages. I have 1 light on my porch, I can convey 2 messages. 2 to the power of n, where n is the number of lights, right? So if we had 3 lights, we could convey 2 to the power of 3, or 2 times 2 times 2, or 2 times 2 is 4, times 2 is 8. So there are the 8, and we could create our own coding scheme. There it is. Right? And instead of saying on or off, we could say, hey, 0's for off and 1 for on. And that's why with computers, we see all these 0's and 1's. All it means is there's some circuit or there's some switch that is on or off. Now, this is the mind-blowing thing about computers. It's a really basic concept that something can be in an on-off state, and it can mean one thing if it's on and another thing if it's off. That's a really basic concept. But computers take that concept and they scale it to the level of billions, right? So being able to check billions of circuits and seeing if those light switches, so to speak, are in an on-off state, and being able to do that quickly, billions of times a second. Holy cow, that's the power of computers. And that's everything in a computer is just a 0 or a 1, which means it's a circuit in some configuration of on or off. And that configuration of on or off means something. Somebody created some coding scheme. So it might mean that, this arrangement of on and off, 0's and 1's, means it's this color red. Or a slightly different arrangements of 0's and 1's, circuits in an on-off state, it's a slightly shade different of red, right? Slightly different shade of red. So it's really a truly amazing concept that this is how computers work, but that's all that's going on beneath them. And that's how we get to 0's and 1's. So if that's new to you, that's awesome, because I love sharing that with people and watching them go, whoa, really? That's amazing. It is amazing. It's totally amazing. So we could do a coding scheme like this, right, where I have the on-off represent letters. And then I could, create, I could have circuits in a certain arrangement of on or off, and I could create a message. So pause the video again right now, and right here, I want you to figure out, what does this message say? So 001 would be B. So I'd put a B here, right? So that's B. So pause the video and figure out what message did I store here with storing certain on-off states. All right, so here's the answer. It's all I could come up with with just the first 8 letters of the alphabet. That's all I could come up with. So there we go. That's kind of interesting. So the computers, the generations of computers, modern computing really started in the 1940s with World War II. And originally we stored our on-off states with vacuum tubes. And you can look up images of like ENIAC, right? And these are like these really old computers from like science fiction movies. But they used vacuum tubes to store on-off states. And so here are pictures of vacuum tubes, right? And those could be checked. Is it in an on state or is it in an off state? And anyhow, right? Like the first computer, the ENIAC, had 18,000. That's it, 18,000 vacuum tubes which could be checked in an on-off state. And then the second generation computers went from vacuum tubes to transistors. Oh, but first I got to tell you, Grace Hopper debugging, right? Wait, where'd it go? Debug. There we go. So moths used to fly into the old computers with vacuum tubes because vacuum tubes were hot and they gave off light, and moths loved that. And so the moths would fly into the computer, and then they would short out the vacuum tubes, and so they would have to go in and debug the computer. Isn't that a trip? They'd actually have to pull the bugs out of the computer. So that's where we got the phrase debugging, getting the bugs out. Cracks me up. So the first generation computers were all vacuum tubes. That's where we stored our on-off state. Second generation computers were transistors. Right? And so we went from vacuum tubes, which would burn out and ran hot and attracted moths, to transistors. And transistors didn't burn out. They were way smaller, right? Like this is the size of a quarter right here, and so a lot smaller, right? Like this would be smaller than a penny right here. And I'd be able to pick it up. I'd hold it in my hand about like that. But they ran cool. You could check them if it is in an on-off state, and they were a lot smaller. And so we started to be able to check a lot more circuits. Are they in an on-off state? And we could start to store stuff. I'm storing the letter A in these 4 light bulbs, circuits, switches, transistors, whatever you want to call them. I'm storing it right here, and they're in this arrangement, so that's the letter A. And literally, when I hit A on my keyboard, there's like 8 switches or 16 switches. They go into a certain configuration of on or off to store that letter A. I mean, that's where it really gets mind-blowing, the scale of it. Like, holy cow, there's so much going on. So first generation computers are vacuum tubes. Second generations were transistors. And then third generations, we went from transistors to integrated circuits. And you could also think integrated circuits as chips, right? And so here's like a chip. And what's inside that chip, what's inside that integrated circuit is a chip, silicon wafer, right? And so here's a silicon wafer. And if you look at silicon wafer closely, so whoa, like check it out. Here this guy's holding a silicon wafer, and on that silicon wafer, they print them onto one big chip, right? They print them on one big wafer, one big board. And by the way, they make this out of sand. Like they make this out of the same stuff that they make fake breasts out of. Silicon, that's it, right? Like, what an amazing substance. Fake breasts and computers. Silicon wafers. So here we have silicon wafers, and they print them all on one big chip. And then you look, and these chips are a bunch of squares, and then they cut out each one of these. So these wafers have a bunch of chips on them. They print them on one big wafer, and then they cut these chips out. And each of these chips can have billions of circuits which can be in an on-off state. So that's a phenomenal accomplishment of humankind, right? We went from vacuum tubes, which were these large things about the size of a light bulb, to transistors, second generation computer, which were like, that big, down to silicon wafer chips, where we store on something the size and thickness of your thumbnail, we are storing billions of circuits which we can write to and we could read almost instantaneously. Holy cow, right? So that's the third generation of computers. And then the fourth generation of computers, a microprocessor, a CPU, came out like 1969, 1970. Intel invented it. Intel doesn't stand for intelligence, it stands for integrated electronics. They were integrating electronics, and they integrated various electrical components into one place, one central location, and they called that the central processing unit. You know, it's just like crazy when you start to see how all this stuff comes together, right? But that's what Intel did. They integrated electronics into the central location, the central processing unit, and they brought together all these things like the arithmetic logic unit, the control unit, the registers, the cache, and they put it all into one place, and they created this microprocessor. It did this processing at a really small level, and they were contracted to develop this, but then they threw the contract away. They said, we don't want your money. We created all this stuff. We created it for you. We're giving it to you, but we're not taking payment because we're keeping this technology, and we're gonna market CPUs and see what we can do with it. And that's how Intel got its start in the 70s. And so there's this dude at Intel, Gordon Moore. Here he is. And in the late 60s, he said, you know what? I am predicting that we're going to be able to double the processing power of computers every 18 months. And since the late 70s, that has held. So you could go to Google and you can search for, is Moore's law still true, right? And you can find out if it's still true because it's starting to waver just a little bit, but then some new invention comes out and like keeps going. So, but every year the processing power is doubled. So we see that like in 1971, the first silicon wafer chip had 2,300 circuits on it, right? 2,300 circuits, transistors. All these words are interchangeable for switch, circuit, transistor. It just means something that could be on or off. But 1971, the first one had 2,300. And now if you look, right, like here in 2008, 2 billion. And if you go and you look Wikipedia, Moore's law, right, and you look at what the current image is, because I haven't updated that slide, but here's the current image, and we're at 2.6 billion, 2011. Holy cow. And the way computers have really, like the last 5, 6, 7, 10 years, really gained a lot of speed, like here in 2007, right? Quad core, dual core, right? So we have dual core, quad core, and that's starting to come on. And so, now not only one CPU in a machine, but multiple CPUs in a machine. And this is only from 2007. And this is why Go is so amazing, right? Because right here, we started to get multiple cores in machines. And before that, we didn't. And all of the programming languages, all of the major significant programming languages were created back here, where there's only one core. So there's been no new language except for Go, which has any viability that has been created to take advantage of multiple cores, right? Except for Go. And that's why Go's awesome. So that's Moore's law. That's the generations of computers. That's how computers work. There's Gordon Moore. It's truly an amazing story. Circuit switches, transistors, and gates, those terms can all be used interchangeably. And I'll let you pause the video right here and read this, right? Because this kind of like helps explain that a little bit. And here's like, that thing, one light, how many things can we represent? So you can pause the video here and check that out if you want. And 2 to the n is the secret to figuring that out. And so if we have 16 lights, we could store 65,000, right? Our coding scheme could store 65,536 possible combinations, right? And if we have 32 lights, it could be 4 billion. Holy cow, right? And so binary digits, when you create an acronym from that, it becomes bits. And so binary is bicycle, biplane, it means 2, right? So we're dealing with 2, and the 2 that we're dealing with is on or off, or 0 and 1, and it's a binary digit. They're digits because they're zeros or ones, and so we call those bits. Awesome stuff, man. And binary digits, that's where we get it, right? And we can measure bits. And so how do we measure bits? So 1 bit is 1 bit is 1 bit is 1 bit. That's it. It's just a single, 0, or 1. If we have 8 bits, we call that a byte. If we have 1,000 bytes, we call that a kilobyte. If we have 1,000 kilobytes, we call it a megabyte. If we have 1,000 megabytes, we call it a gigabyte. If we have 1,000 gigabytes, we call it a terabyte. And now, really, this is 1,024. And the reason it's 1,024 is because that's a multiple of 2. And we have 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024. However, to keep things like kind of simple, I always just say, hey, it's 1,000. But if you want to be absolutely accurate, it's 1,024. So, but it's a lot easier just to remember. It goes from a bit to 8 bits is a byte, and then 1,000 bytes is a kilobyte. So if I have a kilobyte, a single kilobyte, how many bits do I have? That's my next question for you. If I have a single kilobyte, how many bits do I have? All right, so to answer that, like pause the video and see if you can work it out, but to answer that, and need your help, crying kids, all right, be there in a minute, right? If I have a kilobyte, I've got 1,000 bytes, and if I have 1,000 bytes, I have 1,000 times 8, or I have 8,000 bits, right? And so here is like, 1 kilobyte's 8,000 bits. 1 megabyte is 8 million bits. And you can remember a megabyte is a million because M is million and M is mega. So 1 megabyte's a million bits. That's easy. And a gigabyte's a billion. And a terabyte is a trillion. T, tera, T, trillion. There you go. So that's pretty amazing. And you can always go back to how many actual zeros and ones are in this. So when you look at an image, so let me just go look at my computer, and I'm sure I've got some sort of an image here. My pictures, sample pictures, and let's change the way we're looking at that and go to details. And, I don't see the thing, but properties. And here we have, it is 845,941 bytes. Or to figure out how many bits that is, we could bring that into here and multiply that by 8. And I think I need to take the comma out. I don't know how Google works. And so it's that picture has 6,776,528 bits, single binary digits, right? So that's like 6.7 million circuits are in some state of on or off to remember the data for this image. Whoa, there's like 6.7 million single circuits that are in some state of on or off to remember this image. Like, that's amazing. And that's really getting down to the metal. That's like how computers work, that's it right there. So, you could kind of like do these problems right here, and they're kind of good to do just to work about. So on, off, 1, 0, binary digits, bits, machine language. That's all the same stuff, right? We're talking about circuits that are in some on-off state. Machine language is just the language computers speak, which is zeros and ones. That's it. Above machine language, when we talk about programming language, we have machine language, we have assembly, and then we have third-generation programming languages, which is pretty much everything else, right? Like Python, Ruby, Go, PHP, C, C++, C#, all that stuff, Java, right? It's all third generation. So machine language, assembly, third generation language. All right, so I'll let you pause the video here and read this too, just sort of help disambiguate things, help you get a little more insight. And then here we have the power symbol, right? And that's where it comes from. 0 and 1 mean on or off. So that is it. That is it, man. That is how computers work. Those are the fundamentals. In 22 minutes and 22 seconds, you just learned more about computers than the vast majority of the human population knows. Isn't that amazing?